Welcome to the Deep Dive, your shortcut to understanding the research that really matters. Today we're tackling something you probably interact with daily, maybe without even realizing it. Epoxy resin.
Mm-hmm. It's absolutely everywhere.
Right. Sealants, glues, structural components in, well, everything from aerospace to basic construction. Super common stuff.
Absolutely. It's a workhorse material.
But here's the kicker. Predicting when it might fail in the real world. That's a huge challenge. The stresses it sees out there, say in a bridge or a machine part, they're almost never like the simple push-pull tests they do in the lab.
Exactly. Those standard tests, tensile or compression, they give you a qualitative feel, maybe a comparison between materials.
Okay.
But for predicting failure under actual service conditions, with complex multi-axial loads, changing temperatures, you need something more fundamental.
So the simple measures, like how much it stretches before breaking, aren't quite enough for these brittle materials.
Precisely. Epoxies, polymers in general, they don't have much plastic deformation. They don't stretch or bend much before they, snap. So using ultimate strain as your limit, it's just not reliable enough.
Okay, so if deformation isn't the key, what did these researchers focus on instead? What's the limiting characteristic?
They shifted the focus to energy. Specifically the ultimate strain energy density. We call it twalifolus.
Strain energy density.
Yeah. Think of it as the maximum energy the material can soak up internally per unit volume right at the moment before it fractures.
Ah, like its energy storage limit before failure.
You got it. And the whole point of this research was to build a kind of 3D failure map. They call it a fracture locus. It shows how that energy limit, to toologers, changes depending on the exact type of stress being applied.
Okay, section 1 then. The complex world of stress prediction. So moving from simple force to this energy idea. To make that 3D map work, you need ways to describe these complex stresses mathematically, right? Beyond just pulling.
Absolutely.
Yeah.
If you want to design something reliable, you need these mathematical tools. The study uses two main factors, two invariant characteristics of the stress state.
Invariant meaning they capture the essence of the stress regardless of how you orient the part.
That's the idea. The first one is the stress triaxiality factor, denoted by teledollars.
Okay, teledollars, what's that telling us?
So teledollars basically tells you the balance between tension and compression at a point. Is the material generally being pulled apart? That's teledollars greater than 0.
Positive teledollars, more pull.
Right. Or is it generally being squeezed together? That's less than 0. Negative teledollars, more compression. It's essentially ratio.
Got it. So teledollars about the overall pull versus push balance, but stress can come from different directions, right? Not always uniform.
Exactly. That brings us to the second factor, the Nadai coefficient, mu sigma.
Mu sigma.
If the ray tells you about the magnitude and sign, sort of, does anybody describes the shape or the form of that stress state?
Shape. How so?
Well, think of it like this. If a sigma is plus or minus 1, it means the stress state is perfectly uniform around an axis. Like perfectly squeezing a cylinder from the sides or pulling it evenly, that's an axisymmetric state.
Okay, uniform pressure.
But if a sigma is 0, that represents what we call a plane strain state. This often corresponds to pure shear, like trying to slice something, or when the load is really concentrated in one plane.
Right, like shearing a bolt or bending a plate.
Precisely. Now, the interesting context here, as you mentioned, is that engineers know these factors pretty well for metals. Metals often bend and deform quite a bit first.
Yeah, they give you some warning.
They do. But for brittle materials, like polymers, adhesives, how depends on axisoblin and sigma across a really wide range of conditions, that's been much less understood. A bit of a black box, really.
And the study was trying to map out that black box. Okay, section 2, the material, the method, and the math. What exactly did they test, and how did they manage to create all these different stress shapes?
So they looked at two materials. First, just the pure epoxy resin.
The baseline.
Yep. And second, the same epoxy, but reinforced with 10 weight % of titanium dioxide nanoparticles.
TXTiO2 guy.
Okay, TXTiO2. Common additive. Now, creating those specific Quoron, those sigma values, that sounds tricky. You can't just use standard test coupons, right?
No way. Your standard cylinder and compression, that only gives you a tiny sliver of the possible stress states. To map out the whole fracture locus, they needed to get creative. Really creative.
How so?
They had to design and machine these incredibly specialized specimen shapes. Things like bell-shaped specimens. Those are good for inducing shear under tension or compression.
Okay.
Then, thick-walled cup-shaped specimens. Testing those creates a complex state called dishing. And oblique dog bone shapes to get pure plane shear. Plus, yes, standard cylinders for basic compression data points.
Wow. That's a lot of custom machining just to prepare the sample.
It really is. A huge effort before the testing even begins. And then they added another layer of complexity. Temperature. Ah, right. You mentioned temperature swings.
They tested everything at 2 temperatures. Standard room temperature, $25 Certex, and then way down at a pretty frigid $50 Certex.
Minus 50 C, that's properly cold.
It is. And here's a key point for you listening.
Yeah.
Both $25 and $50 Certex are well below the glass transition temperature, the temperatures of these epoxy resins.
Tearless, can you just quickly remind us what that means?
Sure. Tearless is basically the temperature where a polymer flips from being relatively soft, maybe a bit rubbery, to being hard, rigid, and glassy, like glass.
Okay.
These epoxies had T-roll values around $74 to $78 Certex.
Yeah.
So testing at $215 and $5 means they were deep in that glassy state, rigid, brittle.
Which is often how they behave in structural applications anyway, especially in cold environments.
Exactly. It's very relevant. Now, here's where it gets really clever, almost a shortcut. Even with those fancy specimen shapes, the stress inside isn't static.
Right. As it starts to deform or crack, the stress field changes.
Precisely. Tensile and sigma aren't constant right up to the failure point. They evolve. So just measuring the initial load isn't enough.
So how do they track that?
Computational analysis. They use finite element simulation software, specifically ANSYS.
Ah, computer modeling.
Yep. This allowed them to simulate the entire test, millisecond by millisecond, and calculate how tail and sigma were changing right at the point where the crack was predicted to start.
So they could pinpoint the exact stress state at the moment of fracture initiation.
Exactly. That gives you the true energy limit reached under those specific dynamic conditions. It's a combination of physical testing and high-powered simulation.
Okay, section 3. The headline versus the detail. So they did all this complex testing and simulation. Before we get into the really nuanced 3D map, what was the basic story? Did adding those text TiO2 nanoparticles help?
Well, if you just look at the standard mechanical properties, the headline is pretty straightforward.
Yeah.
Yes, adding 10% text TiO2 consistently boosted the strength.
Okay. How much of a boost are we talking?
Quite significant in some cases. The stiffness, what we call the normal elastic modulus E, it increased by about 14% at the cold $50 Certex and 11% at room temp.
Decent improvement in stiffness.
And even more striking was the ultimate compressive strength. That went up by 25% in the cold and a really substantial 35% at room temperature.
35% stronger in compression at room temp. That sounds great.
It does. So the headline reads, reinforcement works, makes it stronger, stiffer. Based on standard tests, you'd say, great, let's add nanoparticles.
Right. So if that's the headline, why all the fuss with the 3D fracture map, the calidollar and mu sigma? Why not just reinforce everything?
Ah, that's the crucial question, isn't it? If we only looked at those standard tests, we might make dangerous assumptions. We might assume that boosting compressive strength means it's tougher all around, under any load.
But failure isn't just about overall strength.
It's profoundly dependent on the type of stress. Now, there is a general trend that holds true. The ultimate energy density. It does tend to increase as the compressive stresses become more dominant. So as the collar decreases, tallurgy generally goes up.
Meaning the more you squeeze it, the more energy it can absorb before breaking? That makes intuitive sense.
It does. But the devil is in the details, especially when you combine different types of stress, when you have multi-axial loading. That's where the simple headline breaks down and the map becomes essential.
Okay, section 4, the ambiguity of the fracture locus. This is where it gets counterintuitive, right?
This is where it gets fascinating. Because while the text TiO2 clearly helps in standard compression, its effect on the actual failure energy under different combinations of TL or infugumenta and at different temperatures, well, it's complicated. It turns out to be ambiguous.
Ambiguous how? Meaning it helps sometimes but hurts other times.
Exactly that, depending on the specific loading scenario. This really highlights why you can't just rely on a standard material data sheet. You ask that question. If I reinforce this for compression, how does it actually behave under shear in the cold? The fracture locus gives us the surprising answers.
Okay, let's dive into those specifics.
Yeah.
You mentioned comparing different stress shapes, different mu sigma values. What about the plane strain or shear case where nu sigma exalts $1?
Right, so under this shear dominant type of loading, the results were really eye-opening. At the warmer temperature, $25 Certex CI, get this, the pure epoxy, the unreinforced one, actually had a higher failure energy density than the reinforced one.
Wait, the nanoparticles made it worse in shear at room temperature?
Across the entire range of triaxiality, they tested for that condition, yes. The reinforcement was actually detrimental to its ability to absorb energy before fracturing in that specific state.
That completely contradicts the compression tests.
It absolutely does. And it gets even weirder when you drop the temperature to $50 Circtex.
Yep.
In the cold, under that same plane strain condition, the reinforced epoxy was better when the stresses were compressive.
Ah, so reinforcement helped if it was being sheared and squeezed in the cold?
Right, but when the stresses were tensile, the reinforced epoxy was significantly worse than the pure epoxy.
Wow.
You literally see a crossover on the graph. Reinforcement helps for cold compressive shear, but hurts for cold tensile shear.
So imagine you have a component under shear in a cold environment. You absolutely need to know if that shear has a slight compressive or tensile component locally to know if your reinforcement is helping or actively hurting you.
That's precisely the level of detail this reveals. It's staggering.
Okay, that's the ambiguous shear case. What about the other extreme you mentioned, axisymmetric compression, where sigma equals $1 This is the uniform squashing, right?
Correct, like perfectly crushing that cylinder.
Yeah.
And here, the story flips again, but towards consistency this time. Under this uniform compression state, the reinforced epoxy resin was the clear winner. It consistently showed a higher failure energy than the pure epoxy.
At both temperatures?
Yes, at both $25 Circtex or $1 Circtex, and across the whole range of tellers they could achieve in that state. So here, under uniform compression, the Tex TiO2 reinforcement provided a consistent benefit. No ambiguity.
Interesting. So it loves uniform compression, hates certain types of shear, especially when cold and tensile.
That's a good summary.
Yeah.
And there was another interesting observation specifically for that axisymmetric compression at a $50 Circtex domain.
Yeah.
At that deep cold temperature, under that uniform load, the material's ability to store energy before failure, $2, it sort of plateaued very quickly. Increasing the compression further, making colors more negative, had almost no additional effect on typical.
It hit its absolute energy limit very quickly in that cold, rigid state.
Pretty much. It suggests that under those specific conditions, the failure mechanism becomes less sensitive to further increases in compressive stress once it's deeply cold and uniformly loaded.
Okay, let's wrap this up. Outro time. So what's the big takeaway here?
Well, the immediate takeaway is that the researchers successfully did what they set out to do. They built these incredibly detailed, comprehensive 3D maps, these fracture loci, for both the pure and the reinforced epoxy.
Maps that chart the failure energy across this huge space of possible stress states and temperatures.
Exactly. And the application for you, the engineer or designer listening, is direct and practical. These dependencies they found, they're essentially lookup charts.
How would you use them?
If you're designing a part or maybe an adhesive joint, you can use simulations or analysis to estimate the specific kind of multi-axial load it's going to see in service, figure out the likely dollar and mu sigma values it will experience. Then you can consult these fracture locus maps to see what the actual failure energy limit is under those specific conditions at the relevant temperature. It allows for much more accurate risk assessment.
Moving way beyond just relying on that simple compressive strength number from a standard test, avoiding those potentially dangerous assumptions.
Precisely. It combats the danger of overgeneralizing material properties, the real-world performance, the reliable life of a component. It hinges on these sometimes ambiguous interactions between the material makeup, the exact stress geometry, and the temperature.
It really drives home how complex material failure can be under realistic conditions.
It does. And maybe a final thought for you, the learner, to chew on.
Let's hear it.
We saw here that adding a reinforcement boosts standard strength, like compressive strength, significantly. But under certain other conditions, specific shear states, especially when cold, it actually lowered the material's ultimate energy absorption capacity, making it potentially more brittle or prone to sudden failure in those scenarios.
Right. The reinforcement wasn't universally good for failure resistance.
So consider this. How many other common structural materials out there, think about concrete mixes, carbon fiber composites, different metal alloys, rely heavily on standard test data for design? Could some unexpected field failures of these materials actually be due to them encountering these kinds of specific, complex, multi-axial stress states where their performance deviates significantly, perhaps ambiguously, from the standard datasheet predictions? It makes you wonder how often these ambiguity zones in material behavior are the real culprits in structural integrity problems.